Okay, so this chapter, RF discharge. So in this chapter, we can know why people use RF power supply to generate plasma. So what is the advantage of RF power supply, or what is the problem that RF power can resolve? Okay. So the first important thing is that if we have placed an insulating material, an insulating substrate in a plasma system, so when the substrate touch plasma, it will automatically form a sheath voltage on the surface of the substrate, or a potential difference between plasma volume and the substrate surface. So there's a potential difference, and this potential difference is also called sheath voltage. Okay. So if we place an insulating material inside the DC plasma, the surface of the insulator will charge up, and then charge up negatively, and then reach a stable condition, so that the ion flux and electron flux come to the surface of the substrate, become equal, so that the charge flux are positive charge and negative charge. Okay, they are neutralized, so that the total charge flux becomes zero. So at this condition, the surface is at a floating potential condition. Okay, and the sheath voltage, or the floating potential, is about 10 volts to 20 volts. So the surface will build up a sheath voltage around 10 volts to 20 volts. It depends on the plasma potential. It depends on the plasma condition. Okay. So sometimes we need a substrate surface with a bias higher than 10 to 20 volts. Sometimes we might need a bias voltage of 50 or 100 volts, or negative, or minus 50 or minus 100 volts, to undergo surface treatment or plasma treatment. So if you use a DC plasma and just let a piece of insulator placed inside the plasma, the sheath voltage cannot reach 50 or minus 50 or minus 100 volts. So in that case, one needs another way to generate a plasma, or to generate a high sheath voltage condition. Okay, so this is the first part, okay, of the importance of the RF power, or RF plasma. And the second thing is about the continuous operation of plasma. Okay, so in this case, if we have placed the insulating material on one electron, or surface of one electron, the insulating material will also charge up at the beginning. The insulating materials will charge up by the capacitive or mechanism. But later on, after the plasma is generated, the plasma will extinguish in very short time. Okay. So if we place an insulating materials on the surface of electron, we cannot run continuous plasma or continuous closed discharge. Okay, so in the next slide, on the next two slides, Chapman explain and analyze this condition, why the plasma cannot be continuous generated if you place an insulating materials on surface of an electrode. Okay, so this slide explains the basic of the capacitive discharge. But in this case, one use DC power supply to generate plasma. So what happened when we use DC power to generate plasma? Okay. And the upper figure is the schematic of the system. Okay, so this part is the power, DC power. This part is the DC power. And on the right side is connected to the one end of the power, connected to the negative polarity part. And at the left end, the electron is connected to the positive polarity and also connected to the ground. Okay. And here is the switch. Here's the switch. So this is a basic circuit for the DC discharge system before one strike plasma. Before the plasma is generated, okay, the circuit looks like this way. Okay. And then after you switch on the circuit, the right side of the electrode will start charging up. Okay. And in this figure, the back side is the metallic electrode, and the front side, this black is a shadow. Is a piece of insulator. It's a piece of insulator. Okay. So this part works as a capacitor. Okay. Because electrical current cannot pass through insulator. So when you at the beginning, when you switch on the brake, the right side, the back side of the insulator, actually the electrode surface on the right side will charge up negatively. Okay. So electron current keep flowing to the back side of the metallic electrode. The electron current will flow to the back side of the metallic electrode. Okay. And at this side, right next to the metallic electrode, the insulator surface will charge up positively. Okay. And the other side of the insulator will charge up negatively. So actually, the surface of the insulator also charge up negatively. Okay. So this is by a displacement current effect. Okay. So this part is negatively charged, and the other side is positively charged or grounded. Okay. So there is a potential difference between the insulating surface and between the grounded anode. Right side is the cathode, left side is the anode. Okay. So based on a basic capacitance or capacitive effect, we can calculate the amount of electrical charge on the surface of the insulator. Okay. So the surface will be charged up, and the total amount of charge is Q on the surface. And Q equals to the capacitance times voltage. Q equals to CV, or C equals to Q divided by V. V is voltage, Q is the amount of charge, and C is the capacitance. Capacitance of this insulating material, and with one side of the electron and another side of a virtual electron. Okay. And we can write this equation in another way. V equals to Q divided by C. Okay. And for this piece of insulating material, the capacitance is a fixed value. So the amount of charge is proportional to the voltage on the surface, or charge up the voltage. Okay. So when we switch on the circuit, and the right side is the cathode, and the surface of the insulator becomes a negative charge, okay, and the other side is grounded anode, so that if the voltage or the potential difference is high enough, if the potential difference is high enough, the plasma will be generated between the grounded anode and the charge of the insulating surface. So there will be a plasma. The plasma will be generated in this region. And once the plasma is generated, we can replug the circuit, because plasma can be considered as a part of the circuit. So the plasma has at least two components. One is the resistance or resistive component, the other one is capacitive component. Okay. So in this circuit, we can add a resistor here, to represent the resistive component of plasma. And we can also add a capacitor here to represent the capacitive component of plasma. And then this is a closed circuit. Okay. So plasma can conduct electricity, but it composed of resistive component and capacitive component. And some other type of plasma consists of inductive component. But in this chapter, we will just focus on the capacitive type of discharge. Okay. And the bottom figure shows the transient voltage curve for this discharge system. Okay. So the horizontal axis is time, and the vertical axis is the voltage on the surface of the insulator. Okay. So at this point, we switch on or close the switch so that the surface of insulating material can be charged up. Okay. So for example, we can charge up the surface of the insulator to a minus or 1000 volt, for example. At this point, minus 1000 volt. So here, minus Vs, okay, means the surface potential of the insulating material. So at time T0, the surface becomes negatively charged, and then plasma is generated. And once plasma is generated, as we have already known, inside plasma there are charged species, electrons and ions. Okay? So electrons will be repelled from the negative charge surface. Ions will attract it. by the negative charge the surface. Okay. So when the cations come to the surface of the insulating material, their positive charge will neutralize with the negative charge. Okay. At the beginning, the surface of the insulating material is charged up negatively. Okay. But the negative charge will be neutralized by the positive ion bombardment, so that the net amount of charge or the total amount of charge will decrease. Okay, so the Q here will become smaller and smaller. And since Q becomes smaller and smaller, the voltage, the charge out voltage, becomes smaller and smaller. So in this region, the voltage, right, from the maximum Vs minus Vs, and then gradually decrease. So this is caused by positive ion bombardment or by the cation bombardment, cation from the plasma. Okay. And eventually, the potential on the negative insulator, on the negative charged insulator, become too small, so that the plasma cannot sustain. So plasma will extinguish, will disappear. So you cannot generate a continuous plasma by DC discharge. If one of the electrode is connected with a piece of insulating material. So in order to remain a continuous discharge, one needs to charge up the surface in very short time, so that the surface will become negatively charged again. So instead of using a DC discharge, people start using AC discharge. And AC is very high frequency AC. It's not like our indoor electricity. In our indoor electricity, the frequency of AC is 60 Hertz. 60 Hertz. So for every second, there are 60 cycles. Positive, negative, 60 cycles. Okay. But in industry, in order to generate a continuous plasma, by using the RF power supply, the frequency of the AC or frequency of the RF must be around megahertz range. Okay. So in Chapman's book, he gave us an example. So if the insulating material placed on surface of the electrode is a piece of quartz, and the thickness of quartz is 1/8 inch. Okay, 1/8 inch. And the capacitance of this piece of quartz equals to 1 picofarad per centimeter square. Okay. So this is a capacitance per unit area for a piece of quartz plate if the thickness is about 1/8 inch. Okay. And then if we apply a bias with the maximum bias voltage of 1000 volt, and we can also control the current flowing through the circuit. So the current density here is 1 milliamp per centimeter square. Okay. So based on these conditions, we can calculate the time to charge up the surface of the quartz plate, and to reach a charge up a voltage of 1000 volt, equals to a 10 to minus 6 second, 1 microsecond. So it takes 1 microsecond to charge up the surface of quartz plate to minus 1000 volt. If we flow current with a current density of 1 milliamp per centimeter squared. Okay, so it takes 10 to minus second to complete a cycle to charge up. So if we use such high frequency of the AC power supply, we can call this as RF, because the frequency falls into a radio frequency region. Okay. And in industry, you can use the frequency, RF frequency a little bit higher than 1 megahertz or a little bit lower than 1 megahertz. Okay. So if you use about 100 kilohertz of power supply, you can generate plasma. And if you use 13.56 or 14 megahertz of RF power supply, you can also generate plasma. But these two types of plasma have different plasma properties. Okay. So for low frequency power supply, the plasma, once it is generated, the ion energy in the plasma and the electron energy inside the plasma will be higher than the plasma generated by a higher frequency. For example, 40 megahertz power supply. Okay. So it depends on your applications. You can choose the plasma frequency of plasma power supply. But usually, in industry, the standard frequency is 13.56 megahertz. Okay. So if we use an RF power supply, we can generate a continuous discharge or continuous plasma. So here, the symbol here is an AC power supply, AC with different frequencies. Okay. In the previous slide, this symbol means the DC power supply. Okay. So if we use RF power supply in a capacitive type discharge, we can generate continuous plasma. And we also need to know the potential or the sheath voltage on the surface of insulating material. Okay. Because at the beginning of this class, right here, we have already known that in a DC plasma system, the sheath voltage on the surface of the insulating material is about 10 to 20 volts. It's about 10 to 20 volts. It's a little bit higher than the plasma potential, or it is equal to the floating potential. But in RF system, we can generate the plasma, and then the surface of the insulating material can be charged to a few hundred volts, or even 1,000 volts. Okay. And here is the analysis of the system. Okay. So the left figure is the circuit of the plasma, RF plasma system. So the left side is RF power supply. Left side is RF power supply. And one end of the RF output connect to the bottom electrode. And it also connected to ground. So at this point, the bottom electrode the potential is 0 volt because it is grounded. Okay. So this part is called RF ground. And the other side of the output, can send out very high voltage. And this side is called RF high. So in RF power supply, there are two output. One is RF high, the other one is RF ground. So usually we connect RF ground to anode and connect RF high to cathode. So this is the basic way to connect the power supply to your system. Okay. And once the plasma is generated in this part area means the plasma. So plasma is part of the circuit. The circuit forms a closed loop. Okay. And in a capacitive discharge system, blocking capacitor can be placed in series with the circuit. So here C is a blocking capacitor. Okay. So in order to generate a capacitive discharge plasma, the circuit needs to contain a blocking capacitor. Okay. Otherwise, if you place two pieces of metal, one is cathode, the other one is anode. If you just use two pieces of metal as the electrode, and if you generate an RF plasma, if the circuit has no capacitive component, the potential of the RF part and the potential of the ground, okay, they will change. The relative potential will change with time. So half cycle, the upper electrode behave like a cathode, and another half cycle become anode. Cathode anode. So in average, both electrodes will behave the same, even though one is RF part, the other one is RF ground, if there is no capacitive component. So usually in the circuit, in the RF power supplies, and later on, you will know there is another hardware in the circuit, which is called the matching network. Okay. So from the power output to matching network, there is a large capacitor, and this capacitor is called blocking capacitor. If both electrodes are conducting, one needs to place a blocking capacitor in the circuit to generate capacitive discharge. Okay. But if you place a piece of insulator on the surface of electrode, the insulator itself behaves like a capacitor, so that you don't need to install a blocking capacitor in your system. Okay. So here is the complete circuit. So here is the plasma, and here is the blocking capacitor. So in the circuit, there is a capacitive component and there is a resistive component. Okay. And they are on the right side, the upper curve is the output voltage from power supply, output voltage. Right? So here the RF part goes through the electrical wire and then connect to this part. So the voltage VA here, V sub A here, equals to the voltage of RF output, RF high. Okay. So the upper figure shows that if you use a square wave power supply, the square wave power supply is just like the pulse DC, like pulse DC power supply. Okay? So the half cycle is balanced negatively, and half cycle is positive, negative, positive. So this type of square wave power supply, so it's actually a pulse DC power supply. So from this figure at time zero here, the VA, the output connect to the VA here. The voltage, for example, is minus 1,000 volt. Minus 1,000 volt. Right? And they apply the negative voltage kept for a certain time, and then switch to positive, plus 1,000 volt for a certain time, and then minus 1,000 plus 1,000, like this way. This is the waveform of the output, output. And it is also equal to the VA here, reading here. And for the ground electrode, the voltage reading is always 0 volt. Always 0 volt. Right. In a half cycle, this half cycle or the other half cycle. Okay. But in this case, for example, at this first half cycle, the top electrode here is minus 1,000 volt, and the ground electrode is 0 volt. So the ground electrode is anode, and the top electrode is cathode. But in the second half cycle, the top electrode is plus 1,000 volt, and the ground electrode is 0 volt. So it looks like the top electrode is anode, and ground electrode is cathode. So for the RF operation, if there is no capacitor, no blocking capacitor, okay, the transient voltage distribution looks like this way. So both electrodes behave anode and cathode alternatively for each half cycle. But if we place blocking capacitor here and generate a capacitive plasma, and then we can analyze the voltage on the top electrode, VB here. So in this case, the V sub B shows the voltage or the potential of the top electrode. And between VA and VB here is a capacitor, blocking capacitor. Okay. So the second curve here, okay, shows the transient VB, the potential on the electrode surface after we place the blocking capacitor. So at time zero here, okay, the plasma is generated at time zero. But before plasma is generated, the surface of the electrode is charged up to minus 1,000 volt. And it is just like the figure in this slide. Okay, so the surface is charged up to minus 1,000 volt, and then plasma is generated, and cation and electron bombard the surface of the electron. And since the potential of the electron is negative, so the surface will attract more cation, and then the potential of the surface will drop. Okay. So in this figure, okay, so the surface initially charged up to minus 1,000 volt, and then because of the positive ion bombardment, the potential of the surface of the top electrode decrease. For example, it might decrease to minus 800 volt only. Minus 800 volt only, right? And at this time point, right, the polarity of the ion power supply reverse, okay? Because the output here changed from minus 1000 volts to 1000 volts. So there is a difference of 2000 volts. 2000 volts. Okay. So for example, the surface of the top electrode changed from minus 800 volts to 1200 volts. So it will jump up, like this way. Okay. And when the top electrode is charged up, and in this half cycle, actually the top electrode is charged up positively. So in this half cycle, the surface of the electrode will be bombarded by electron. And in a previous chapter, the nature of plasma, in the chapter, we have already known that electrons travel much faster than ions in plasma. Okay. So that the electron flux in this half cycle is larger than the ion flux in the other half cycle. Okay. So even though at the beginning the electron is charged up positively, but the positive charge will be neutralized by the electron bombardment very fast. Okay. So the potential of the top electron might change from 1200 volts and then drop to less than 400 volts. And then at this point, the polarity of the ion output change again. So that, for example, the surface of the electron, the potential of the electron change from 400 volts to this point minus 1600 volts. Okay. So these things happen. So at this half cycle, right, the electron collect positive ion, and another half cycle, the electron collect electrons. Okay. Since the electrons in the plasma have a much larger velocity than ions, so the neutralization rate in this half cycle is faster. So after a few cycles, eventually the top electron becomes negative charge, very high negative charge, and the ground electron keeps at 0 volt. Okay. By the top electron in this negative polarity region, the bias voltage is very large. And in the positive region, the bias voltage is rather small. So that the shape of this curve is not symmetry. So in average, the top electron will become, in average, negative charge compared to the ground electron. Even though half cycle is negative, half cycle is positive. But in the negative charge cycle, the bias voltage is much larger than the voltage in the positive cycle. So the cathode, the top electron become effective cathode, and the ground electron become effective anode. Okay. And the bottom curve, okay, that shows the transient current curve. Okay. So after a few cycles, the surface of the top electron has already built up negative charge, so that the potential, the negative charge surface will repel electron or decelerate electron. So after several cycles, if we check each cycle, in the negative cycle, the ion current collected, or the ion charge collected, equals to in this cycle, electron current or electron collected. So after a few cycles, the surface will not keep charging up, but rather it will become a stable condition. Okay. So this is the analysis of the RF system if one use a pulse or a square wave power supply. Okay. And in industry, most RF power supply use a sinusoidal form, so that the output voltage follows a sine wave rather than a pulse DC type. And so the output voltage for the RF power supply started from 0 volts and increase gradually to the maximum. For example, plus 1000 volts, and then decrease to 0 volt to minus 1000 volt, like this. So this is one cycle. Here's another cycle. And the waveform follows a sinusoidal wave, sine wave. Okay, so later on we can see the equation. You can use the sine wave, sine omega t, to represent the output waveform of the RF power. And in this slide, if you use square waveform of the the power supply, the voltage, the change of voltage on the surface of the top electron looks like this way. And eventually, after several cycles, the top electron experience very high negative bias in this half cycle and small positive bias in another half cycle. And if we change the power output form to a sinusoidal form, so here is the output power, output voltage versus time, or the voltage VA reading here. And for the voltage on the electrode surface, after passing through the blocking capacitor, the voltage reading, the VB, look like this way. It still looks like a sine wave. Okay, but in average, for the output voltage curve, the average voltage is 0 volt, because half cycle is positive, half cycle is negative. Okay, so the average voltage is 0 volt. But on the surface of the insulating electron or the metallic electron after passing through a blocking capacitor, the average voltage will become negative. So all the curve shift down. Okay, and this voltage reading is named DC offset. So the average voltage of the top electrode equal to V DC offset. But for a half cycle, the positive half cycle, the voltage reading looks like this way, and here's another half cycle. And if we take a close look, we can find out only in this small region, the electrode surface is positively charged. But in this large region, large time period, the electrode surface is negatively charged. Okay, so this is for the top electrode. And for the ground electrode, the voltage is always equal to 0 volt. 0 volt. Okay. Okay, any question? The behavior of the I-part electrode and ground electrode. So from this figure, so actually in this cycle, in this half cycle, in this small region, the top electrode behave like anode. So actually it's still changing from anode, cathode, anode, cathode, anode, cathode. But the time period of the anode is smaller than the time period for cathode. Okay, let's take 10 minutes break.